Now, with that out of the way, let me introduce our speaker, Nihar Shah. He's a professor in the Machine Learning and Computer Science departments, and he'll be talking to us today about battling demons in peer review. So with that, Nihar, do you want to take it away?
Sure, yeah. First of all, thank you, Isaac, and thank you, Magdalene, for organizing this seminar series. So today I'm going to talk about some problems in peer review that our group is addressing. And if you work in machine learning or AI, you might be somewhat familiar with this. Your experience might be somewhat familiar with this cartoon that you see on the slide. But more generally, not just in ML or AI, but more generally in computer science and well beyond in many fields of science and engineering, peer review is a major challenge. So there's this very nice article by Drummond Rennie in Nature a few years back, which says that peer review is a human system. Everybody involved brings prejudices, misunderstandings. There are biases, there are inefficiencies, there is some corruption, and all in all, the article says that peer review is unscientific. In fact, survey after survey after survey of researchers in a wide variety of different fields shows an overwhelming desire for improving peer review. And with this goal, the work here looks to tackle the systematic problems or demons that exist in peer review using principled and practical approaches. So we are establishing theoretical foundations, which is what I'll primarily focus on in this talk. And we are also having real world impact. So in this talk, I'll cover 5 topics. And you can consider this also as an outline for the talk. I'll go into details of the first topic of subjectivity. I'll go into the second topic of miscalibration in some detail. And for the last 3, I'll just give a very brief overview. And I'll ask you to catch me offline if you want to chat about any of them. Now, throughout the talk, please feel free to interrupt me if you have any questions. Just unmute and ask. All right, so let's discuss this issue of subjectivity. It's very well known that in peer review, different reviewers have different opinions about the relative importance of various criteria when making decisions. As an example, let's say there is this green reviewer on the left who thinks that novelty is not really useful unless there is an improvement over the state of the art by at least 10%. On the other hand, most of the reviewers think that novelty is extremely important because it can lead to big breakthroughs in the long run. So now if a paper comes along which has really novel ideas, but has only a mediocre improvement over the state of the art, if it goes to the green reviewer, it will get rejected. On the other hand, most other reviewers would accept it. So this is kind of not really fair because the decision for the paper depends on something which is entirely exogenous to the paper. Everyone agrees that this paper has novel ideas and it offers a moderate improvement over the state of the art. But the green reviewer weighs novelty differently as compared to the rest. And hence the final decision would depend on that weighing. So the key question that we ask here is, how do we ensure that every paper is judged by the same yardstick? And of course, we want it to be a good yardstick. So here's the a little more formality in the problem setting. We assume that whenever a reviewer reviews a paper, the reviewer is asked to judge the paper on some K pre-specified criteria. So these criteria could be things like originality, relevance, writing clarity, and so on. The reviewer is also asked to provide an overall score to that paper. Specifically in terms of notation, if a reviewer I reviews paper J, then the reviewer gives a vector xij, which is a vector of length k, as the criteria scores. So these are the K criteria scores, and we'll call Xij as the criteria score vector. The reviewer also gives Yij, which is a scalar, and this is the overall score given by this reviewer to the paper. Now we'll normalize all the scores and assume they lie in the interval 0 to 1. Now we'll make the assumption that every reviewer implicitly in their mind has some mapping, some function that maps the criteria scores to an overall score. The only assumption we are going to make about this mapping is that it's coordinate-wise non-decreasing. So for example, if let's say the value of technical significance increases, everything else remains the same, then the overall score should not go down. Each reviewer can have an arbitrarily different such mapping, so it can be entirely subjective. Any questions so far?
I have a question.
Yes.
Are we assuming that this mapping is deterministic? As in that these criteria summarize all the information that's going into the overall score?
Yeah. So what we are assuming is that there is no exogenous criterion. That is, the program chairs have set upon this K criteria, and this is kind of the universe of criteria.
Okay.
Now, you're right that there might, and this is an interesting question as to even detect that, hey, given this review data, were these K criteria sufficient, or are the reviewers having something else in mind? That's something that I don't know how to solve, but presently we'll assume that this is the universe.
All right, thanks.
Great. Other questions? Please ask. All right. So in terms of this formalism, what we need is a common mapping for all papers, a common mapping from the criteria scores to the overall scores. So in the current system, the overall scores are obtained by applying each individual's reviewer's personal mapping, whereas what we need to find is a common mapping for all reviews or all papers. In order to do that, we'll take a data-driven approach of quote-unquote learning a mapping. So what do I mean by this? Let me first describe a very high-level idea behind the approach. First, we'll collect all the review data. So we get, for every review ij, we get xij and yij, which is the criterion score and the overall score. And then, based on all of this data, we'll somehow learn a mapping. So we'll call this learned mapping as f hat. And now assume somehow you learn this mapping f hat, which is assumed to be a community consensus of how we should map the criteria scores to the overall scores. And then in every review ij, we will recall that the overall score in that review, the yij in that review, had been obtained by using the reviewer's personal mapping. So what we'll say is, hey, let's not use that. Instead, let's use f hat and apply f hat to that criteria scores xij in that review. And let's use f hat of xij as the new overall score. And from then on, the program chairs can make their decisions however they want. We'll not look at that component. So the key question here in this approach is the second bullet. That is, how do we learn this consensus mapping f hat? So here's the framework which we'll use for this. So to see this framework, first of all, for just the purposes of this talk, let's make a simplifying assumption that all papers are reviewed by all reviewers. The reason I'm making this assumption is that life will be much easier for me in this presentation. However, the resulting algorithm that we finally get is more general. And as you can see, we will also use this on real data a few slides later. So now to see this framework, let's look at what data we have. So we can write down our data in the form of two matrices. Each matrix has reviewers as rows and papers as columns. Now the matrix on the left is the matrix of criteria scores, that is the xij's, and the ijth entry of the criteria score matrix is just the criteria scores given by reviewer I to paper j. So that the ijth entry is just xij. Likewise, the matrix on the right is the matrix of overall scores, and the ijth entry of this matrix is yij. That is the overall score given by reviewer I to paper j. So this is the data that we have. Now for a moment, let's think of an ideal world where all reviewers are identical, everything is very nice and so on. In which case, you might have a single function f such that f applied to any value in this matrix, in the criteria score matrix, will give you the corresponding value in the overall score matrix. Right? This is an ideal world where there is no subjectivity, there are no other issues. Now, of course, the world is not ideal, and this is the problem that we are dealing with. So in this framework, what we do is, inspired by empirical risk minimization, we find a mapping such that it best approximates this ideal relationship. In particular, a learned mapping is called f hat, and it's the minimizer over all functions in a certain class script f, which I'll define in a moment, of the loss between f of the criteria score matrix and the overall score matrix. Now, this class of losses are called the LPQ losses. They're associated to the standard LPQ norm over matrices, and I'll also define this in a minute. So now, in order to fully specify this framework, I need to specify two things. One, what is this function class script f? And second, what is this loss or the class of losses that we are using? Before that, I'll pause and ask any questions. Please feel free to unmute yourself and ask.
I had a general question about whether I mean, the other thing we do is we trust the expert more than the non-expert. Is that going to factor into this?
So we're not explicitly factoring, but as you'll see, the algorithm here is easy, that you can just reweigh the experts and non-experts however you want. So for example, if we just look at this slide, for each entry, you can include an additional weight, multiplying that entry, and that will factor in these experts.
Okay.
Great, other questions, please ask. All right, if not, I'll go ahead, and again, please feel free to unmute yourself and interrupt if you have questions at any point. All right, so let me now first specify this function class script f. So this function class is easy to describe. We just set this to be a collection of all coordinate-wise non-decreasing functions. That's it. Yeah. So for example, again, if technical strength increases, nothing else changes, then the overall score should not go down. Note that there is no assumptions of Lipschitzness or convexity or linearity or anything. Okay. Now I need to specify this class of loss functions, and these LPQ losses or these LPQ norms of matrices are a very natural matrix extension of the standard vector LP norms. So the LP norms that we all use over vectors is associated to one parameter p, which takes values in 0, 1. Now this matrix extension, which is the LPQ norm, naturally has two parameters p and q, both of which take values in 1 through infinity. For those who may not be familiar with this LP norm, LPQ norm, let me define it with our example. So you have this matrix and you want to compute the LPQ norm of this matrix. What you do is first look at the first row of the matrix and compute the LP norm. So this is your standard vector LP norm. Then in the second row, compute the LP norm and so on. So for every row, compute the LP norm, write down the results. Now this set of results form a vector. You take that vector and compute its LQ norm. Again, the standard vector LQ norm. And the result is the LPQ norm of this matrix. Any questions? Okay, so the LPQ norms are used in a variety of different applications in signal processing, information theory, machine learning, etc.
I have a question actually. So are we, in this calculation, are we relying on the reviewers, you know, the function that's the hidden function that's known to them, are we relying on that being deterministic, or would this still do a good job even if it wasn't deterministic? I guess because we sort of all know it's not really quite deterministic.
Right. So that's a good point. And here we are not making that assumption at all, right? So at least so far, when we are computing the LPQ norms, or rather, or also in this ERM style framework here, we are just considering the best fitting function. So that function can be noisy, can be stochastic, or it can be deterministic. That's not really something that we are really looking at. Now, initially, I had mentioned that their outcome is monotonic, and that's something that, you know, we don't necessarily require that exact statement. For the purposes of this talk, you can think of it as being deterministic, but as you'll see, we'll not really use that. So it can be stochastic or an arbitrary. So
Okay, thank you.
okay. So this LPQ norm, again, so this framework has not assumed anything about their specific functions. Now, in the LPQ losses, now these are used in a lot of works in various areas, and different papers, if you read them, they make various choices for the values of P and Q. Now, if you go and actually read the justification for their specific choices of which loss function they used, they're usually or always heuristic. That, hey, we think something and hence, you know, we thought this is the best choice and so on. But as many of you know, the choice of the loss function can really influence the outcomes of the learning process. And therefore, here we want to take a principled approach. And so the key question that we ask here is, can we determine in a principled manner which specific loss function in this big LPQ norm class should be used? That's the key technical question that we are asking here. Now, in order to answer this question, we'll take an axiomatic approach. So for those who are not familiar with an axiomatic approach, this approach is popular in economics and social choice theory. And the way it works is as follows. So we'll consider our general problem, and then in that problem, we'll identify certain special case scenarios that are easy for humans, for you and I, to reason about. After identifying these special case scenarios, now you and I will establish certain necessary conditions or axioms which we think are useful in this setting, or rather which we expect from the outcomes. Based on these necessary conditions or axioms, the goal is to narrow down the choice of possible loss functions. So currently this LPQ norm class is a big class. P and Q can take values, any real value in 1 through infinity, and we want to narrow down this choice. So what's the special case scenario that we'll consider here? The special case scenario that we assume is that any paper gets the same criteria score from all reviewers. So for example, let's take paper 1. So in our notation, it got X11 from reviewer 1, X21 from reviewer 2, X31 from reviewer 3, and so on. So these are the criteria scores that it received. And here we'll assume that X11 equals X21 equals X31 and so on. This is the special case we are considering. Likewise in paper 2, the special case we'll consider is X12 equals X22 equals X32 and so on. So the special case has, for every paper, all the X's are equal. So now for any paper under this special case scenario, the identity of the reviewer with respect to the criteria score is irrelevant. And so we'll just drop the reviewer subscript to simplify the notation. And henceforth, for paper 1, we'll just let X1 denote the criteria score vector obtained from any reviewer. Likewise, we'll let X2 denote the criteria score vector obtained by paper 2 from any reviewer and so on. Any questions? Okay, so under this special case scenario, now we'll establish 3 axioms, which I'll try to argue are quite natural. The first axiom is what we call consensus. It says that suppose there exists some criteria score vector X and scalar Y, such that in the data you see that all reviewers are mapping X to Y. Then your learned mapping F hat should satisfy this. That is, you want F hat X equals Y. The second axiom is what we call dominance. Now I'm going to describe this only informally here, and I'll go into this in much more detail in 2 slides from now. Informally, dominance says that if there are 2 papers, say A and B, such that we are all in agreement that, hey, paper A, based on the current review data, is at least as good as paper B, then we want the learned mapping F hat to respect that. That is, we want F hat of XA to be at least as much as F hat of XB. And finally, the third axiom is strategy proofness. And I've written the formal statement here. It's a bit of a mouthful. So let me just tell you the higher intuitive level of what's happening here. So let's say I'm a reviewer, and I know that you're going to use some algorithm which will use my reviews and other reviews in order to learn this mapping F hat. And I know that this mapping F hat is going to be considered as the community's consensus for how to weigh different criteria. And it's also going to be used for the decisions of various papers and so on. Maybe it might be used later on in other conferences, etc., and so on. So now what I really would like to have is to get this learned mapping F hat as close to my own mapping, my personal mapping as possible. That is, if, let's say, I prefer novelty to empirical performance, then I would also like the learned mapping F hat to reflect that. What strategy proofness says is that this should not be, what strategy proofness says is that it should not be possible for a reviewer to manipulate the overall scores that they provide in order to bring the learned mapping closer to their own mapping. So are there any questions on either of these axioms? Yeah. Please ask.
I have a question about axiom 3. So it looks like you're saying it should be strategy proof with respect to the overall scores, but not making any limitations on strategy proofness with respect to the criteria scores.
Yeah. So we are considering this special case where the criteria scores are said to be all equal. So in this very, very special case, which you are considering, somehow all reviewers are in the same agreement over the criteria scores, and now they differ in their overall scores. That's where this comes from. There's another point about this, which I'll come to in a slide from now, in a 1 or 2 slides from now. Great, other questions, please ask. Okay, so recall that our goal is to choose one loss function from this, or rather our goal is to consider this big class of loss functions and try to narrow down the choice of possible loss functions, which will help us in choosing finally one loss function in some principled manner. Towards that, we establish these 3 axioms. And in fact, we show that in this big class of all LPQ loss functions, there is exactly one loss function that satisfies these 3 axioms. And this is the L11 loss. There is no other loss function which satisfies these 3 axioms. Now, in terms of the negative result, we show that strategy proofness is violated when Q is greater than 1. And this is closely related to the fact that medians are robust, whereas other LQ norms are not. Consensus is violated when P is infinity, Q is 1, and dominance is violated in the remaining parameters. And in the next slide, I'm going to go into much more detail of this dominance. And I'm going to do that for 2 reasons. One reason is that I haven't introduced this formally, so I'll go into more details. But the second reason is also that at least I personally found this result to be quite paradoxical. So I'm excited to go into the details. Before that, coming back again to Isaac's question, so if we put the additional requirement that we also want strategy proofness with respect to the criteria scores, maybe it will turn out that L11 is still robust, or maybe it will turn out that we have nothing. Right? So if you put additional constraints, then in some sense we might make the problem strictly worse in terms of now getting nothing at all. That's why L11 still might be a good choice. Okay, so let me go into more details of dominance. And on this slide, I'm going to do it I'm going to provide to you enough intuition about it with the help of an example. Through the slide, I'm also going to ask you a couple of questions. Okay, so let's consider P equals 2, Q equals 1. That is, let's consider the L21 loss. Now, what does the L21 loss mean? It has a very nice and intuitive interpretation. The P equals 2 means that we just take the standard L2 or Euclidean loss over every reviewer. And then Q equals 1 means that we just add them up. So that's the loss. Right? The loss is computed by just taking the L2 loss over each reviewer and then adding them up. So it's a very intuitive loss. Now let's see what dominance means here and how it works. So let's consider this example where you have 2 papers, you have 3 reviewers, and K equals 2. So you have 2 criteria. Okay. Now let's say the criteria scores for paper 1 are given by this X1, which is 1/4, 3/4. So all 3 reviewers give the same criteria score vector X1 to paper 1. And let's say that the criteria score vector for paper 2 is X2, which is 3/4, 1/4. Now let's say these are the overall scores. So reviewer 1 doesn't like either paper, gives a 0 to both papers. Reviewer 2 gives a score of 1 to paper 1 and 0 to paper 2. And reviewer 3 gives a score of 0 to paper 1 and a score of Z, some Z, which is strictly smaller than 1 to paper 2. Now here's a question for you all, and please unmute yourself and respond, or you can feel free to respond in chat as well. So here's a question. Suppose you are the program chair of this conference, and this is all the data that you have. Then, based on this, suppose you have to accept exactly one paper. Then which paper would you accept? Paper 1 or paper 2?
Paper 1, right?
Isaac says paper 1. Anyone else? Charlie says paper 1. Anyone else brave enough to respond? Okay. So if you see here, the criteria scores for both the papers are symmetric. There's 1/4, 3/4, and 3/4, 1/4. And now suppose z equals 1, then you see that the overall scores are also symmetric for both papers. But now what we're doing is making z strictly smaller than 1, which makes paper 2 strictly worse. And hence it's intuitive to accept paper 1. Are there any questions or counter arguments? No, okay. So in this sense, paper 1 dominates paper 2, and hence we want the learned mapping f hat to respect that. So we want f hat of x1 to be at least as much as f hat of x2. Now let's see what happens when we actually try to learn under the L21 loss. Learning under the L21 loss is closely related to what's called the Fermat point of the triangle. So if you are not familiar with the Fermat point, here is how it is defined. So consider any triangle, and now consider any point in the space of that triangle. Compute the Euclidean distance from that point to all 3 vertices, and then add up these 3 Euclidean distances. Now the point in the entire space which minimizes this total Euclidean distance from the 3 vertices is called the Fermat point of that triangle. Any questions? Okay, so now with that, it's quite easy to show that in fact, for the example on the left-hand side, f hat of x1 comma f hat of x2, that point, is exactly the Fermat point of this triangle shown below. The 3 vertices of this triangle are exactly the 3 rows of the overall score matrix on the left. Again, keep in mind, this is when we are learning under the L21 loss. So the vertices of the triangle are 0z, 0, 0, and 1, 0. Okay, now let's see how the Fermat point of this triangle behaves. So for the moment, let's consider z equals 1. In that case, the Fermat point is exactly 0.2, 0.2. Okay, so we can compute that. The key point here is that the Fermat point is symmetric about the 2 coordinates. That is, the x coordinate equals the y coordinate. Now, here's a question for you all. Suppose we do the following. We just take the top vertex of the triangle, the 0z vertex, and we reduce z. So we bring that vertex down and we make z equals half. Then in which direction do you think the Fermat point will move? Again, feel free to unmute yourself or type on chat. Just take a wild guess. Charlie says down.
To the left.
To the left. Isaac says left. Any other guesses? Just guess. So it turns out that the former point moves both left and down, but much more left than down. So when z equals half, the former point is now 0.12, 0.15. And so now, since f hat x1, f hat x2 was this former point, we have that f hat of x1 is strictly smaller than f hat of x2 under this learning under this L21 loss, which violates what we wanted on the left-hand side. So now the definition, so this was for an L21 loss and under this specific 2 papers, 3 reviewers, etc. The general definition of dominance and the general proof construction, etc. is all a generalization of this basic idea. Any questions? Okay, so now what we did was just for fun, we tried to see how this learned mapping looks like in real data. So we took data from the ICHCAI 2017 conference, and in that conference, each review had 5 criteria and then 1 overall score. So we learned this mapping f hat on this conference data. And what I'm about to show you are representative cross sections of that function. It's important to note that what I'm about to describe is not a formal hypothesis test, but representative cross sections based on eyeballing. Okay, so this is just for fun. So what we saw was that in terms of the criteria of writing and relevance, we found that if either of them were really bad, then there was a significant downside. If they were really good, then this was appreciated. And then in between, there was a big plateau where it's almost irrelevant. We also found that the technical quality and significant had a pretty high influence on the overall scores, and the influence is approximately linear. And then the originality had moderate influence. So this completes the part on subjectivity. I'm very happy to answer any questions.
Actually, I had a question. Is this, how are you getting these scores? Are these scores the before PC discussion scores or?
Yeah, so in these large AI and ML conferences, we don't have an individual, personalized PC meetings or anything. So how it works is the following, that here the reviewers will provide their scores, and then the authors can give a rebuttal to the reviewer response. And based on the rebuttal, the reviewers can change their own scores. That, I gave a strong reject, but my point number 5 was wrong, so I'm giving a weak reject. So that's how it works. And then finally, you have what are called area chairs who will make the decisions based on some discussions with the reviewers. So these scores are at the point where the reviewers initially gave their scores, then they saw the rebuttal, and according to the rebuttal, they adjusted their own scores.
But did they adjust just the overall score, or do you think, I mean, my opinion is people get lazy and they don't bother to adjust their criteria.
Yeah, that happens a lot. So by the way, one thing is, at least what we found in various conferences is that most reviewers are lazy, that they won't change the scores. So I would say a bulk of this is identical to their initial scores.
Okay.
So they might change the comments, the text comments that, hey, okay, I agree, but they may not change their scores. Now, even in that, what fraction had changed their overall scores versus criteria scores, that's some data that we don't have.
Mm-hmm. And they also got to see each other's reviews, right, and scores?
Yes. But again, after the initial process, only a small fraction actually changed their scores. Okay, Phil or anyone else, do you have any other questions?
I'm good.
All right, then let me move to the second part, which is about miscalibration. And miscalibration in scores or in ratings is a very well-known phenomenon. For example, let's say you go to the emergency room and the first question that the nurse would ask you is, rate your pain level on a scale of 1 through 10, right? Now, what does a 7 really mean here? Your 7 out of 10 might be very different from my 7 out of 10. And that's this problem of miscalibration. And this problem is very well recognized in the literature. For example, Mitliagakis et al. Say that a raw rating, say of 7 out of 10, in the absence of other information is potentially useless. Amar et al. Say that the rating scales and individual ratings are often arbitrary and inconsistent across users. And Freud et al. In this landmark paper on rank boosting, they say that using rankings instead of ratings is very important when you have to combine the opinions of different people, since these different people might use completely different ranges of scores to express identical preferences. So now, in order to address this problem of miscalibration, there have largely been two approaches in the literature. The first approach is to assume simplified models for miscalibration. And there are various works on this approach, which have rather simplistic models. For example, saying that the miscalibration is usually just a scale and a shift. Now, the algorithms for calibration, which are based on these models, were actually tried out in certain big conferences in ML, and anecdotal evidence says that these did not work well. For example, John Langford, who's the ICML 2012 program chair, says that they experimented with this and they generally found it significantly harmful. A second approach is to instead use rankings. So now either after you get the ratings, you convert each reviewer's set of ratings into a ranking, or you directly collect rankings. And this is commonly believed to be the best option if you cannot make any such simplifying assumptions on the miscalibration. So the key question that we ask here is this folklore belief true? That is it possible to do better using the ratings as compared to using the induced rankings with essentially no assumptions on the miscalibration? Now, is there a question on chat? Is it possible? Pravesh, by the way, feel free to unmute yourself and ask. I may not monitor the chat. Is it possible to discuss what they found harmful with respect to the calibration? Yes, so as I said, this was anecdotal evidence. That is, what they did was they applied this algorithm and then they saw the result. So they saw that, hey, earlier the reviewer was giving a strong accept, but now this algorithm says that there should actually be a weak reject. And then they look at the paper, they look at the reviewer, they'll look at the text of the review, and they'll say, hey, this does not look like a reject. This reviewer is saying accept, clearly saying accept. It doesn't make sense. So that's the kind of anecdotal evidence I'm talking about.
I have a question as well.
Yes.
So sometimes certain people are more likely to review papers they're going to accept, or more likely to review papers they're going to reject. Oftentimes reviewers can choose what they review based on the abstract or something. Wouldn't that look very similar to miscalibration to an algorithm?
Yep, absolutely. And that's a problem, right? In peer review, we have very small sample size. And therefore, well, if you're reviewing 3 papers and you give 3 accepts, it could be that you got 3 good papers, right? Or it could be that, you are very lenient. It's hard to distinguish. And that's what makes this an extremely challenging problem.
No, I think I was asking a slightly different question. So you might have 2 reviewers, one who's reviewed 100 papers and another who's reviewed 100 papers. But one reviewer, they only review papers if they're confident from the abstract that they're pretty likely to want to accept it. The other one only reviews papers if they're pretty confident they want to reject it. So sample size won't help you in this sort of circumstance.
Sure, and that can also be a problem. that's kind of orthogonal to what we're going to discuss in this talk though.
Okay, got it. Thanks.
Great. Other questions? All right. So we're looking at just the fundamental question that is it possible to do strictly better using ratings than induced rankings, even if you have no such simplifying assumptions on the miscalibration. And to illustrate this, and just in the interest of time, I'm going to give you a very toy 2x2 example setting. I call this 2x2 because there are 2 papers and 2 reviewers. The 2 papers have some true scores, say Z star A and Z star B. And these 2 reviewers can be miscalibrated. So now here is how we model their miscalibration. The first reviewer has some function f1 implicitly in their mind, such that if they are asked to review some paper I, whose true score is Z star I, then instead this reviewer will output f1 of Z star I. Likewise, the second reviewer in their mind has some function f2 such that if given some paper I with the true score Z star I, this reviewer outputs f2 of Z star I. Okay, so this is their miscalibration. F1 and F2 are of course not known to the algorithm which processes this data. Okay, and in particular now, since we didn't really want to make much assumptions, we'll say that, hey, let an adversary choose Z star A and Z star B. And let an adversary also choose this miscalibration functions F1 and F2. The only constraint we are going to put is that F1 and F2 are strictly increasing. But otherwise, this adversary can do anything that they want. For example, the adversary can say that the first reviewer always gives scores between 0 and 0.1, and the second reviewer always gives scores between 0.9 and 1. Now here we assume that each reviewer reviews one paper and each paper is reviewed by one reviewer. And this assignment is done uniformly at random. So now the data that you have access to is the assignment about who reviewed what and the score given by each reviewer to the respective paper that they are reviewing. And the goal is to find which of the 2 papers was the better paper in terms of their true score. So now here's a question for you all. So here we are saying that each reviewer gives the score to the paper that they are reviewing. And note that each reviewer is reviewing exactly one paper. Now suppose that instead of giving scores, each reviewer is asked to rank all the papers that they are reviewing. In that case, how well would we be able to achieve this goal? Any guesses?
We have no information at all. It's completely hopeless.
Great, perfect. Right, so as Isaac says, we have no information at all, right? Because what do you mean by ranking of just one paper? Well, this paper is rank 1 irrespective of its quality. And so the information that you have is vacuous, and this amounts to just random guessing, right? You'll be correct with probability half. So for the purposes of this toy 2x2 setting, our question reduces to the fact that under this setting with scores, can we do strictly better than random guessing? Now it turns out that if you have deterministic estimators, you can't do any better than random guessing. But there is a randomized estimator that uses scores that strictly outperforms ranking or strictly outperforms random guessing. And here's the estimator in this 2x2 setting. So what this estimator does is it takes the scores given by the 2 reviewers, computes the difference and takes the absolute value, then does 1 plus that value divided by 2. And with this probability, it will accept the paper which received the higher score. Okay, so this is the estimator. Now, let me do a proof by example. So let's say that the miscalibration of reviewer 1, F1, is x by 2. So this reviewer is very strict, always gives scores between 0 and a half. Whereas let's say the miscalibration of reviewer 2, which is F2 of x, is 3 plus x by 4. So this reviewer gives scores between 3/4 and a 1. And let's say these are the true scores for the two papers, 0.2 and 0.6. Now let's say if reviewer 1 was reviewing paper A, they would give F1 of 0.2, which is 0.1. If reviewer 1 was reviewing paper B, they would give 0.3. If reviewer 2 was reviewing paper A, they would give 0.8. And if reviewer 2 was reviewing paper B, they would give 0.9. Now, of course, the key challenge is we don't have access to this entire table. What we do have access to is just one of the two assignments. So let's consider this blue assignment. Now, under this blue assignment, here is what the estimator will do. So look at the difference between the two scores, which is 0.1 and 0.9. Take 1 plus absolute value by 2, and that's 0.9. Now it will see, hey, paper B has received the higher score. Paper B receives 0.9, whereas paper A receives 0.1. And therefore, I will pick paper B with probability 0.9. Likewise, under the red assignment, you compute the difference 0.3 minus 0.8, take the absolute value, 1 plus that by 2. And now you get that here, paper A has received the higher score. And so you accept paper A with probability 0.75. The key difference between these two assignments is that under the blue assignment, the output is correct. Right? Paper B actually has a larger value. Whereas under the red assignment, the output is wrong. But now you observe that the probability of the output being correct, which is 0.9 under the blue assignment, is strictly greater than the probability with which the output is wrong in the red assignment, which is 0.5. And hence combining these two, you see that you're on average correct with probability strictly more than 0.5. So this is the intuition behind this 2 by 2 example. Any questions? Okay, there are no questions. Then we come to the last three parts, which I'll be presenting just one slide each, just to give you an idea of what this problem domain is. And I'm very happy to chat with you offline if either of you are interested. This next part is about noise. And by noise here, I specifically mean poor reviews due to inappropriate choice of reviewers. So in these large ML and AI conferences, the assignment of reviewers to papers is done primarily in an automated fashion, for example, using this system called TPMS. However, both in theory and practice, we have found that this kind of matching system is unfair, especially to interdisciplinary papers. And so the key question that we ask here is, how do we assign reviewers to papers in a manner that ensures fairness and some sort of statistical accuracy? And here, so we have a new assignment algorithm which has strong theoretical guarantees on these properties. Importantly, real-world evaluations independently by a group at UMass in top 3-tier conferences, as well as at ICML 2020, shows that this algorithm achieves a significantly higher fairness as compared to the existing algorithm. So now theory meets practice. And moreover, if we look at the objective that this TPMS original algorithm was trying to optimize, our algorithm has kind of a comparable value. So this has nice theory and empirical properties, and this algorithm was actually used in ICML this year for doing the assignments. The next part is about strategic behavior. And I'm going to talk about two problems here. The first problem is that if you are a reviewer, then if you give a lower score to the papers that you are reviewing, it will improve the chances of your own paper getting accepted. And this is a malicious incentive which people have shown actually leads to such behavior in practice. A second challenge is, suppose you have two people in the system, one author and a reviewer. The author tells the reviewer that, hey, you bid on my paper and try to get it to review, give it a really positive review, and then instead I'll do some other favor for you. This also happens quite a lot in these conferences. So the key question is, how do we mitigate these manipulations? And here again, we have theoretical results, algorithms, and experimental evaluations. And we also deal with these issues of biases. For example, there is a lot of debate in various communities about single versus double blind reviewing. For example, theoretical computer science is largely single blind. And there is a lot of debate that, hey, single blind, where the reviewers know the author identities, can lead to biases with respect to gender, race, the fame of authors, and so on. But then another counter question which is asked is, hey, but in my research community, where is the evidence of any such bias? And so the key question that we ask is, how do we rigorously test for biases in this peer review process while still ensuring a good review process? And by the last line, I mean, we can't just do a randomized controlled trial by randomly giving reviewers papers and so on. So again, we have an experimental methodology, statistical tests, and theoretical guarantees. I'm happy to chat about it offline. So to conclude, there are many sources of biases and unfairness in peer review, and there is an urgent need to revamp peer review. And in particular, in the ML and AI domains, you need to do it at a large scale. Beyond just individual papers or research grants, there is a lot at stake, including careers and scientific progress. And our work, we established the theoretical foundations for many of these problems and are having a real world impact. So beyond what I discussed, if you're interested, we have many more theoretical and experimental results much more recently. There are a lot of open problems in this area, which are really exciting. They span the spectrum from theoretical problems to applied to conceptual problems. They're really challenging because of the complexity of this application. But if addressed, then they can be really, really impactful and directly affect all of us. So with that, I'll stop here and I'm happy to take any more questions. Thank you.
All right, let's unmute and applaud for our speaker for a bit.
So Nihar, I know you said ping me offline, but let me ping you for one of the questions online.
Yeah, ping.
So just to get a sense of what ideas might be there here, how do you tackle the first kind of malicious reviewer instead of, okay, so some TCS conferences, for example, just don't allow reviewers to submit, and that's one way to remove that incentive. Is there a way in which you could hope to remove that incentive without letting the reviewers also not submit?
Yeah, great. So in ML and AI conferences, everyone is a reviewer. You don't have enough reviewers, so that's not at all possible. Right. So now here we build on what's called an impartial mechanism, and in particular, what's called a partitioning method. So I'll tell you very briefly what this is. It's very cool, like if anyone wants to understand. It's a very simple mechanism. It's been proposed in the literature for peer grading, and then we extend it to peer review, which has many other complexities. So what's at the heart of this idea about this partitioning-based mechanism? So it's simple. So the problem that we are trying to prevent is that I, as a reviewer, am incentivized to lower the scores of the paper I'm reviewing, so that in a relative sense, my paper goes better. So here in this mechanism, what you do the following. you take all the reviewers and all the papers, and at random, say uniformly at random, you divide them into two groups and somehow assume that the papers authored by reviewers in the first group, all those papers end up in the second group and vice versa. Now reviewers in the first group review papers in the second group and vice versa. That's the basic idea.
Okay.
The key challenge in peer review is you can't do this uniform random breaking and so on, because each person reviews multiple papers. Each paper is authored by multiple reviewers. And then you can't arbitrarily assign any reviewer to any paper, because you have to keep in mind who are the experts, who are not, and so on. Those are the key challenges beyond the peer grading applications, which was considered earlier.
Yeah, no, that's very nice. Yeah, that makes sense.
Great. Other questions, please ask.
I was wondering if there was a short description of the new auto assignment algorithm that was an improvement on TPMS.
Yes. So here is how the assignment procedure works in these AI ML conferences. So it happens in two phases. In the first phase, what you do is you take all the papers and all the reviewers, and for every reviewer paper pair, you compute what's called a similarity score for that pair. So this similarity score is a number between 0 and 1, and a higher number means that this reviewer is more relevant to this paper and is envisaged to do a better job on this paper. Now, there are a variety of ways in which this similarity is computed. For example, comparing the text of the current paper and the reviewer's past paper, the bids, and so on. Okay. So now that's the first phase, and here you compute these similarities. Our focus is the second phase, where we take the similarities as input, and we want to assign the reviewers to the papers in a manner that can lead to the best possible, the highest possible similarities in some sense in the assigned reviewer paper pairs. The way TPMS works is it does the following. It sets up this optimization problem where you want to compute the assignment such that the sum of the similarities of all the assigned reviewer paper pairs is as large as possible. That's the Toronto paper matching system, TPMS. Now they're trying to optimize the sum over all the papers, and hence it results in the problem that it favors, for some papers it will try to assign all 3 good reviewers at the expense of some other papers which will have all 3 poor reviewers. Instead, what we say is the following: simply change this to do a min-max approach. That is, instead of having the sum similarity, you look at the paper which is the worst off, and you try to maximize the similarities for that paper. Subject to that, you try to maximize the similarity of the second worst off paper, and so on. So that's the new optimization problem.
I see.
And then this is NP-hard, but then we have an algorithm to solve this in poly time with some approximation guarantees and so on.
Okay, makes sense.
Great, other questions?
Yeah, so I have a more philosophical question, but
Yeah.
so does anyone look at the actual quality of the review beyond the scores, like, the actual recommendations that people say? Because I mean, philosophically, right, the peer review system is supposed to make your paper better or to highlight some issues in your research, right? So I was wondering if anyone has looked at the actual, text that people return in these reviews beyond the scores, and how useful, like, what is the estimation of how many good reviewers we have to begin with?
Yeah, so that's a very good question. A lot of people have looked at, there is a non-trivial amount of literature looking at the text of the reviews and the decisions and so on. And this exists much more in the other sciences. not so much in CS, but other sciences. CS is slowly catching up there. But then, it's not easy to define what a good review is and what a bad review is. It's very challenging. For that, I don't know of any work which directly says that, hey, we have 38% of bad reviewers and 62% good reviewers. The way people often measure this is in terms of, say, either things like inter-reviewer agreements, how much the reviewer decisions correlate with each other, or they do some sort of randomized, they do some sort of controlled trials. For example, they do things like you take a paper and then you introduce some errors. Now the original good paper is given to a random subset of reviewers. The erroneous paper is given to the other subset of reviewers. And then you compare the two, right? How many are able to detect it here and so on. They've done other things like they've taken papers which are accepted to prestigious journals and then given it to some other reviewers and asked, hey, review this, what do you think? And then they found that 80% of those papers were rejected by the second reviewer. So they've largely done these things. I'm not sure if that's exactly what you were going for, but actually quantifying a good or bad review is quite challenging. I don't know how to define that.
Yeah, no, I assume that. Yeah.
Great, other questions?
Actually, yeah. This is a huge topic, and you could talk for hours, but I'll keep it brief. So about this reviewer issues, right? Like you've been thinking about this from an incentive perspective, and it seems like apart from altruism, there is not much in store for reviewers in terms of incentive. And so, like, do you have thoughts on that? Like, clearly, okay, we may not be able to measure good and bad in a concrete way, but it's clear that if we were able to develop an incentive system for people to invest more time and effort into writing reviews, they'll likely be better.
Absolutely. I fully agree with that. There are a few things that have been tried out. So for example, there is this, I think it's called Publons. So it's not popular in CS, but in other disciplines, where you get credits for doing reviews. So you have some sort of a score and leaderboard and all of that. So that's one. Within CS, for example, some conferences have said that you'll get a free registration, or top 30% will get awards and so on. The problem there are also challenges in both these approaches. So in the Publons approach, in my view, there are major challenges. For example, let's say that you are a senior person already, you have tenure. Well, you don't really have much incentive to get those points, right? What matters to you is your papers or your research or something else. But you have some extremely junior folks who really want to shine somewhere. So they'll just accept to review 100 papers, may do some shoddy job, and then get their name on top of the leaderboard. So there the incentives are still not that well aligned, unfortunately. In terms of the ML conferences, so the feedback which is used to rate the reviewers is the area chair feedback. So the area chair says that, hey, this was a good review, this was not a good review, and so on. Again, this is based, what I'm about to say is based on anecdotal evidence and my personal experience, that these are extremely noisy. And it's hard to figure out, it's easy to figure out really, really bad reviews. But then, weekly bad reviews are quite hard to figure out because the area chair themselves has not read the paper, so they don't have enough context. A second thing which people have thought about is getting author feedback, because the authors know the paper. So the author will say, hey, this was a good review, this was a bad review. And there is actually literature on this where people have found that the author's feedback is extremely biased with respect to whether the reviewer accepted or rejected the papers. You give a flowery positive review, the authors will say, wow, what a great review. If you have valid criticism, still very frequently the authors will say, hey, this was a terrible review. So these are all these issues which happen. I don't have a good solution. I don't know a good solution yet.
Have you thought of like just making the reviews public? At the end, the reviewers have to sign off their name as like a document that will be available for posterity.
Yeah, great. So there are two. So what you're referring to is what's called open review. And actually open review has two different meanings. Both are associated to what you said. So in ML, this open review is on this website called openreview.net. It's a conference management system where, say, conferences like iClear are hosted there. So there, all of the reviews are all public, right? So as soon as you submit a paper, that paper is public. The author names are hidden, but the entire paper is public. As soon as a reviewer submits a review, that's also public. The reviewer identities are hidden. Just the content of the review is public. Then when the authors respond, that's public, everything's public. So except for the reviewer identities, everything's public. That's one. I don't know how well that has incentivized things and so on. Maybe it has. I don't know of any study which has kind of quantified things. Actually, I do know people have done some studies where they've measured basic things like the length of the review, and they found that to be similar in open review versus non-open review. The second kind of open review that you said is people sign off with their names. And that's something that some journals have tried out, not in CS, but elsewhere. The problem is that many people are reluctant to do this because if they want to give a reject or a negative review, it's very difficult because, there can be retribution. Especially if a junior person wants to reject some senior person's paper, you can't do that. And so that leads to a big bias there.
I see. Yeah, it's a longer discussion. I'll definitely send you an email, but yeah, this was really informative.
Happy to chat. Yeah. Great. Other questions? If not, then I guess we can call it a day and thank Isaac and Magdalene again for organizing this seminar series.
And let's thank Nihar as well for the great presentation.